Thanks for the intro. And this is my first time either speaking at Phosphagy or visiting Kosovo, so I'm really thankful for both of those opportunities. I'm going to tell you a little bit about Diagonal, which is a geospatial data science consultancy that I co-own, that we work on problems for the urban and built environment. And talk a little bit about some of the projects that we work on. From there, some software that we built to help work on those projects. So generally, we work with people who are trying to shape interventions in places, so regenerate cities or public space. And so our clients are typically local governments or urban design studios or large property developers. And our goal is to kind of bring some quantitative data science to the problems that they're dealing with. We're a steward-owned company, so we are owned by employees, and we have a legal structure in place that guarantees that that will always be the case and holds us to some ethical standards about how we use our technology in the built environment. We're a very small multidisciplinary team. I'm the software engineer. We have Gala, our data scientist, Claire, product manager, Simona, our designer, and Veronica, our urban planner. And so we all work together on these kind of projects. And typically we work on projects where the organizations we're helping have found the data science challenges too difficult to work with in the past, largely due to scale and complexity. They don't have the in-house expertise to deal with it, and so we will help them out, typically by kind of building interactive tools. So just a couple of vignettes of the kind of things that we work on. This is for a public wayfinding consultancy based in London called Applied Wayfinding. And they look at interventions in public space to help increase the number of people who walk. They had quite a qualitative understanding of how people navigate in space. And one thing they realized is that it's easier for people to navigate when they have quite a large field of view and can see landmarks. And so on the contrary, where you're in a small enclosed space with little visible landmarks, it's harder to navigate. And so in those situations, they would introduce wayfinding techniques, public signage, placemaking to make it easier to navigate. And so we help them out by bringing some kind of data to that problem by, in this case, the area of London around St. Paul's, but we did it for the whole of the city to kind of build heat maps of how far you can see at a particular point and whether or not you can see any landmarks. Another little project we did was with Hassel, a public space architecture studio, working on a park in Mexico City called Ecoducto. That is, if people know the High Line in New York, it's kind of like an inverse version of the High Line. The park is trapped between two major roads. And in some cases, you have to get to the park, you need to build a bridge into the middle. You can see the park there in the top left. And in other cases, the park is at the same level as the road, and so actual access is easy. And so when you're kind of building and planning that park, there's a trade-off between how expensive it is to build an entrance to the park at a particular point, because whether or not it's grade separated or needs a bridge, versus who actually has access to that park. And so that's quite a complicated problem. And so we did a little bit of modeling, and the modeling we did here is kind of indicative of most of the problems that we work on. We don't think there's a perfect machine learning, data science-based answer to most problems. Most of the problems that we work on, you know, out of the solution space, 80% of the solutions will be just not useful at all. And then the 20% that are left are actually like, you know, they have quite complex trade-offs, both that you can understand through data, but also social and political trade-offs too. And so our general approach is to use data science to whittle away those 80% and then build interactive tools to let people who know about the project in particular explore that data in real time. And so here we built a little bit of tool where we modeled what are the 20% of the best possible solutions in terms of equity of access and value for money across all the combinations of access points to the park that you could build. And then we built tools to let people play and explore that data interactively to make a more informed trade-off. And lastly, a project we're working with the south of Scotland on at the moment about inner city regeneration, where they're interested in looking at urban policies to bring back vacant land into use. And one of the questions they have there is, what is the current level of access to services that people have? And so we built some interactive tools to let them play with and understand that problem. While a lot of our work is for clients, and so we can't talk about it, these examples are all public if you want to look at our website, diagonal.works, there's more details there. And when building these projects, we often have to kind of deal with building kind of interactive visualizations and tools. And we couldn't really find a great fit in the existing world of tooling. And so we built our own. We built our own set of analysis tooling that we call B6. It's something that we use ourselves every day in our day-to-day work. And because we work in the built environment space, any project that we work on, the impact of that project on the communities that surround it is going to far outlast our involvement in it. So we think ethically, it should be possible for other people to redo the analysis and build on any analysis that we did as part of that project. And so because of that, we open sourced the analysis work that we do to let people do that. If you also work in analyzing data for the built environment, maybe you'd like to use it. It is very much a work in progress. I think this is the first time we've talked about it publicly. But hopefully people will find some use out of it. There's a link to our GitHub repo, diagonal.works/B6. There's a README there that tells you all about it. The easiest way to kind of get started with it is to run it under Docker, which will run a little server on your own machine running our application. And then you interact with it through a Python client library that you can install at the bottom. If you've never used Docker before, it's a little tool that makes it very easy to run virtual machines on your machine. I'll just give you a little high-level overview of the architecture of how it works. We have kind of input data, so typically we work with OpenStreetMap as a base map because then it's easier for us to share the analysis afterwards. And we will ourselves improve OpenStreetMap coverage and contribute it back if we need to for a particular project. But then also we will tie in data from third-party sources, often local government data, but also some client-provided data. And so we have a suite of tools called B6 Ingest OSM, B6 Ingest GDAL, etc., that take input data and they transform that input data into a compact version of the data that includes the data itself, but also some search index information that's necessary to allow fast search over that data. So you start off with the source data and you end up with what we call an index file that has the data and all the search indices that you need on top of it. We have a backend server that then maps that data into memory and it exposes that data via HTTP2, a gRPC connection, so that you can access it from a Python script or Python notebook. So typically you'd have the B6 server running on your local machine or possibly a cloud VM, and then you talk to it via a Python script or notebook. But for kind of interactive investigation and just to see what data is there, we do have quite a rudimentary web interface that the server shows you as well. and when you've ingested data, what you end up there, it's effectively it's a read-only version of your data that can be loaded very, very quickly into memory. The server itself does let you modify, and it does that because it can very kind of cheaply create a mutable layer on top of that data. And then you can kind of change it and run analysis on top of it. It doesn't get ever persisted, but often for analyses, what we do have to do is say, how would access to this particular park changed if we built roads here or changed these parking lots into residential usages? And so that's supported by this concept of a mutable world. We start with a basic version of the world. We run a bunch of analysis that changes that world in some way, and then we recompute analysis and export the data. And so we use B6 kind of in three ways day to day. Firstly, we use it as a web interface to explore the data that we're working with. We'll then often analyze it using Python or an IPython notebook and export the results of that analysis as GeoJSON. And then we'll load that GeoJSON into a bespoke visualization that we build. Or when we're working with much larger data sets. So for example, the project we're doing that covers the whole of Scotland, we use B6 just as a library. It's written in Go, and so you can link it into a Go application. We use it as a library to build interactive tools directly on top of it. And we designed it to kind of make use of an environment which is kind of the opposite of the internet computer talk that was just before the one I'm talking about now. We designed it for kind of modern machines which have a lot of RAM and many, many CPU cores. And so the whole application assumes that you have a decent amount of RAM available, lots of CPU cores, and you have to kind of distribute your computation over those CPU cores. And maybe that's your own machine, or actually maybe you're just doing the analysis on the machine, and the B6 server you're running on a cloud virtual machine somewhere. Typically when we're doing analysis, if we're working at kind of the scale of like a large city like London or something like that, we'll just run everything on our own laptop. If we kind of move up to the continent level, then we'll run B6 on a cloud VM and connect to it remotely. I'll just show you a little bit of a screenshot of a web interface to give you a feeling of the kind of things, what happens if you run the Docker container. So you can click on a point, gives you the lat long for that point, shift click, and it will tell you the features at that point. This is mainly the OpenStreetMap base map. We can do reachability analysis, and so you can say what buildings can you reach within 1,000 meters walking of that particular point. And we can do things like the visibility sightline analysis that you saw earlier for some polls. That's kind of built in if you want to play with it there. If you can convert things to GeoJSON and export those, and so that's the workflow that we would typically use kind of day to day if we're building on top of things. My original plan was to demo this live off my laptop, but I didn't see how to do that while holding this mic, and so I very quickly made some screencasts during the coffee break. So a little bit about the data model of how we represent data behind the scenes in the B6 server. We use kind of what's basically a superset of OpenStreetMap's model. So we have point features, which are a place on Earth, and they have a unique identifier. We have paths, that's a bit of linear infrastructure, and along a path can be points with identifiers, or they can be plain lat longs, which is useful if you're importing data that is quite complex in terms of geometry, but doesn't necessarily need to be linked to other bits of the graph. And then areas, sets of closed paths, again with a unique identifier. And much like OpenStreetMap, connectivity in our world model graph happens by sharing points with the same identifier between pieces of geometry. Relations, like in OpenStreetMap, group different types of features together. Each feature has a unique identifier, and that's composed of two things. It's got a string namespace and then a 64-bit integer value. And so the namespace lets us load into the basic server data from lots of different data sources, but then connect them together and kind of make one connected view of the world. So you'll see, for example, in the middle there are the identifiers that you get with OpenStreetMap features, but then we'll also, just examples of things when we load in data from like the NHS or the Office for National Statistics in the UK. Normally, the 64-bit integer value we derive directly from the underlying source data set, and so that's how we tie our data and our version of the world back to other sources. So, for example, for OpenStreetMap, it's just the underlying ID. Features have tags, just like in the OpenStreetMap model. Some tags are prefixed with a hash, and those hashes mean they're indexed for searching, and so that when you can quickly search for any feature that has a hash in front of it. The geometry indexing that we used is based off S2, which is part of the Go standard library. It's basically a way of hierarchically indexing squares on the face of the Earth. I guess what's interesting about it is that both it and all the geometry calculations we do are spatial. So internally, all of our points are not projected onto a 2D plane. They're 3D points on a unit sphere, so we don't have to worry about projections so much. And then the way that we make use of parallelism is lots of our operations will return back a list of or a collection of features, and we support running across those collections in parallel through a map operation. So here's like a little worked example of what that might look like. Let's say that I want to find a nice bench to sit at in the area that we were just looking at, because I like benches. First of all, benches aren't shown on the base map, but if you just enter a tag in there, it will show you where the benches are. These are all dynamically generated vector tiles. That's our starting point, and so we can say, where are all the benches that are reachable by 500 meters walking from that particular point? There we are. And then let's say we want to say, I'll just drag that around so we can browse around and look at them. Let's say I like benches where you can see something. So what I'd like to do is work out what the visible area is from each of those particular benches. So I can map across those benches with the same sightline operation we saw earlier, and then get back a new collection that has the areas, but we want it ordered. So I can say, where are the top 3 benches that I'd want to sit at? And the top one, let's see where the top one is. What does it actually look like? Looks pretty good, yeah. Looking out over the canal, that's a nice place to sit. So that's an example of how you kind of tie the bits together. In Python, what that would look like is you connect to the local, your B6 instance, and then we have an API. What's interesting about this API is that the functions, they typically don't return you the answer straight away, because it's not returning an answer. It's returning kind of an expression that will give you the answer once it's sent to the server. And so the way you send it to the server is that you pass it to this connection instance that we have earlier. And so, for example, here we are. You can turn an expression that counts the number of benches into the number of benches by just passing it to this connection instance. Reachability, you can do using this. The commands that you saw used in the little web interface there, there's a one-to-one relation between that and the Python code, because it's exactly the same. The Python API is actually auto-generated from the same place. And then we can map across those benches that we found there to work out the areas. And then ultimately, when you evaluate it, that collection we just saw of benches gets returned as a standard Python list of tuples that you can work with. So we want to go in the future, because it's super early. There's a few things that we can do internally that aren't in the interface. So for example, I didn't mention how you actually change the underlying world model. So we want to kind of expose that in the web interface. You can do it through Python, but not through the interface yet. And often what we do at the moment is you end up doing a lot of visualization in IPython, drawing graphs from results of B6. And so we want to add some kind of simple graphing directly into the web tool itself, so to kind of pull back that loop. Yeah, so it's very early days, but if you want to, if you'd like to take a look, we're always happy to hear feedback and love to hear how people like to use our things. The talk is there, the code is there, and I'm andrew@diagonal.works if you want to drop me an email. But otherwise, thanks, and I'm happy to answer questions if people have any.